Right, so this presentation is going to focus on the feedback for the Section A part of the mock. So just before we kind of dive into the actual mark scheme itself, here's just a checklist which you may want to use as part of your revision over the weekend to make sure you're kind of happy with the key topics that could come up. So yes, it's a very kind of abstracted view. Within each of these topics, there might be quite a bit of content to cover and revise, but it does give you a kind of a structure, something to work through in terms of improving Section A and your understanding of it. I've linked the booklet names, so you can see red booklet, yellow booklet for regular languages there as well. And obviously, I mean, particularly in regular languages, you've got a whole host of questions in the back of that booklet, and the mark schemes have been posted onto Teams as well. There's also the past paper questions that you've been working through in the revision sessions from Easter onwards as well, which are all available on Teams for you to use as part of your preparation here. Okay, so yeah, you might want to use this as a bit of a tick list, and you can cross them off as and when you feel you've revised them well enough for some of the key topics that will be likely to come up in Section A. Yeah, so let's move on into the mark scheme. So question A was a binary search, wasn't it? And you had to indicate the order in which these elements in the array would be visited if you were running a binary search looking for Richard. So a little bit of a reminder, because you kind of, you're expected to sort of know that algorithm, and there's an example of one in the top right hand corner. And yeah, the answer to this, well, the key thing to remember is this calculation of the mid value, which happens on each iteration, and then that determines the actual element in the list that will be inspected and compared against the value that's been searched for. And some people got that wrong. So if you see the calculation here is the beginning plus the last div2, okay, and so some people missed that. So in this case, we've got a beginning pointer pointing at the beginning of the array. This array is indexed from 1 and pointed to the end. So we add the two together, 1 plus the 15, and divide by 2 and we get 8. So we go 1 for Philip. That's the first value that we compared against Richard. Obviously, Richard alphabetically is greater than Philip, so this will kind of trigger the beginning pointer to be updated, won't it? Because we know now that we can chop off the first half of the list, and the beginning pointer will update now to point at 9, and we'll sort of loop round in this iteration, and we'll calculate a new value for mid, which in this case is 9 plus the 15, and that gives us 12 in total. And so we go and visit Timothy next. Okay, and then here we're back at the check, aren't we? This time Timothy alphabetically is greater than Richard, so it means this time we're going to have to update the rear pointer, and we're going to lose the bottom half. We're going to chop off the bottom half of the list now, and our rear pointer will now point to Richard. Okay, we'll go back through, we'll calculate a new mid value. So in this case, 9 plus the 11 is 10. And so Ravi is the next person that gets checked. So number 3. And then, yeah, we've still not found Richard, have we? We're going to basically, again, because Richard is alphabetically greater than Ravi, we can chop off this half this time of the list. And our front pointer is going to now point to where our rear pointer is. So they're both equal to the same value. So on the final iteration, we come through and we've got 11 plus 11, and div2 is 11. And we found Richard there. Okay, so that was the mark scheme with 4 going in for that particular one. So a recap there, but most people got the initial calculation correct. And if you did go wrong on this question, it was usually because possibly not taking into account the beginning value for this array being 1 as opposed to 0 like it would be if you were programming it. Okay, I'd say 95% of you are happy with this question in terms of binary search being the answer here, the log of n. And then the answer for the maximum number of comparisons, just to remind about how you work that out. So let's say, for example, this list was 137 names long, I think is what's in the question, isn't it? Just remember that process, because we did get a range of answers here. So just if you follow this process, you can't go wrong. So you basically start off and you divide 2 until you hit 1, and then you've just got to remember to add that one extra comparison on at the end, a bit like we did in the previous example, actually on the first question, to get your total number of comparisons. So 137 div 2 68, 68 div 2 is 34, 34 div 2 17, 17 div 2 8, 8 div 2 4, 4 div 2 2, and then 2 div 2. Right, I've kind of hit my base case there, so I've got 7 comparisons if I count this up. 1 2 3 4 5 6 7. Remember to plus my 1 for that final comparison. Gives me 8 in total, and that was why that was the answer. Okay. Right, so the next question moved on to queues, queue data structures, and we're definitely dropping some marks here. So definitely a good place to spend a little bit of time revising. You could well get a question similar to this in the exam on Monday, where they ask you to write a pseudocode pseudocode method for maybe like an on queue, a dequeue, or a push, or a pop, or even a peek operation if it was a stack, for instance. So in this case, we had a circular queue, and I'm just jumping on a question here. You'll notice from what you've got in front of you. To look at the logic and what the pseudocode should be in this particular example, and then hopefully it makes a bit more sense then to go back to the previous questions to work out the actual pointer values that are required for you to identify. So yeah, so this is a circular queue, isn't it? And you've got the deck of 52 cards, and this was what the mark scheme looked like, and a lot of people were getting sort of 2 or 3 marks. So it's kind of what did you miss, and what could you have included? And in some cases a little bit of understanding, because it was a circular queue. Okay, and if you remember, with a circular queue, we've basically got a pointer, we've got a front pointer, which is looking at the first index, the first index in the queue, so where items are going to be removed from. And then we've also got a rear pointer, haven't we, which is going to be looking at the back of the queue, and where we're going to add, well, it's going to be used when we add new items to the queue. So we've got the front here and the rear over here. And I think the question you guys have got is a dequeue operation, isn't it? A dequeue operation. So the first place you could lose marks for was this test, which you might remember. It's really important to include an error checking test, basically, to see if the queue is empty or not. So if it's empty, then we needed to report an error message, and you got 2 marks for that. Really, you got 1 mark for the check, and 1 mark for the output of the error message. Obviously, if the queue's not empty, then there is an item to dequeue. And so the key thing here is to recognize is the front pointer that we're concerned about, because we were moved from the front. And in this case, just outputting the value at that particular front pointer would have got you credit, or returning that value stored at that particular index in the array would be fine. This was the most common mark that people did get. So most people recognize that obviously part of a dequeue operation, you needed to decrease your queue size by 1. That was fine. And then it's this bit where we start to run into into a few problems as well, which is the incrementing the front pointer, which is fine. So incrementing the front pointer by 1. So obviously once Jordan's been dequeued, in this instance, then the front pointer now needs to update. So for the next dequeue, we're going to take Sam and remove index 2 from the array in this particular instance. So that's fine, but it was a circular queue, wasn't it? So at a certain point in time, this front pointer has got to wrap around and point back to the start again. And that was the thing that people missed. And in this particular mark scheme, they did that by saying, well, if the front pointer is greater than 52, because obviously you've dequeued your final element, your 52nd element, your 52nd card. Well, there isn't, you'd have an out of bounds exception, wouldn't you, if you then tried to run this dequeue method again. So you needed to reset that front pointer to point back at the first index again so that it could continue. And that was where the final mark was. There were different ways of doing that. Some people use the mod function as well, but I think that's the most straightforward one to implement to get that to work. So just while we're here, I mean, like I said, they could ask you to do this for an on-queue operation, in which case, hopefully, sometimes it's helpful just to sketch out a mini array perhaps and just work out what the pointers should be doing. But if I just go back to where we started again on here, just important things to note that are different. So you're still going to have an error checking for on-queuing, but rather than saying if it is empty, you're going to need to be checking to see if the queue's full or not. So that's one subtle difference if we were on-queuing. The other thing is, of course, the pointer. So this is going to need to happen first, actually. Okay, so the increment of and it's not going to be the front pointer, of course, when we're on queuing, it's going to be the rear pointer, because at the minute we'd be overwriting, the final person in the queue. And what we need to do is point to the next blank space. So that needs to update first, and then we can assign a value into that position afterwards. So these lines would kind of switch around with one another, if that makes sense. But everything else stays the same. You still need the rear pointer to wrap round as well. So the rear pointer would still need to wrap round there as well. Okay, so it's just making sure you're happy with that, and being able to do that for, if this was a stack, would you be happy to write a push and a pop and a peek method as well? And if you remember, with a stack, you only have one pointer. You only need a pointer that points to the top of the stack for a pop or a push operation or a peak operation. So those subtle differences that you just need to be aware of, but you still need to have the error checking for stacks as well, of course. Okay, so that's where people lost marks. Here was the actual mark scheme, and you can check through. There you can see some the versions are doing the wraparound. So rather than doing the if statement using the mod function, you just need to remember to +1 on this one because of the index starting from 1. Which caught a few people out who did use mod there. Okay, but other than that, they were the kind of the key questions here. I've spotted one more difference, obviously for the on queue. Obviously, that would be increasing the queue size, so an increment of the queue size. Okay, so a good piece of revision that you could do is a little activity there, and I'll sort of mention it in a minute, is the pseudocode exercises for stacks and queues, where you sort of write your own custom queue and your own custom stack. And yeah, I'll just remind you of that in a second. The question that came before the writing the pseudocode for DQ was here, and it was just updating these pointers. Well, as we've just done the recap on that, here we were removing 12 cards, weren't we? The front pointer currently is set to the top of the pack, the 10 of spades. So as we've already discussed, that's the only one that's going to get updated when we're dequeuing. So we're basically just going to +12 onto what the value is that it's currently at, and that was 13. The rear pointer isn't going to change because we've effectively taken these 10 cards off the top of the pack, so that's not going to change. It's change, and the queue size, of course, is going to decrement by 12 because we've removed 12 cards from the pack. So I think if people lost the mark there, it was that one that was the issue. Okay, and then for the second one, we're now on queuing, aren't we? And we're putting 3 cards back into the pack. And again, where people went wrong here was, it was a circular queue. Okay, so remembering it was a circular queue, and obviously when we're on queuing, it's the rear pointer that matters. The rear pointer currently is 52. So because of the wrap round feature, that should update and wrap round to point at the first value. And then we're going to be updating the rear pointer once there, twice, and then for the third card will be on queued into position 3. And then obviously we're going to be adding 3 cards back into the queue there, and obviously for on queuing the front pointer doesn't change. Okay, so that was that. The mark for the first question here, we've sort of worked through this slightly backwards, but never mind. Is I could give you credit as long as you said for the queue first in, first out, I could just give you a mark for that. But on these kind of questions, I do like you to sort of link it to context a little bit. So you can see here, values need to be taken out of the data structure from the opposite end to which they're put in, or the cards removed from the top are added at the bottom of the pack. It was making that link there. So anytime you get a chance to discuss the operation of a queue or stack, make sure you get these acronyms in your answer at least, and ideally try and relate your answer to the context as well once you've done that. Okay, these were the pseudocode exercises that I was just reminding you of. They're in your red programming booklet. You should be able to knock out a stack or a queue in a matter of minutes these days. And if you remember when you did this in class, you made a simple queue that could hold 5 integer values and then could wrap around. But it'd be a really good way just to revise the actual methods for those data structures. Okay. One other thing that we've not talked about for a while, just taking a punt really on something that's in the EAD document, possibly a question on depth first or breadth first traversal of a graph. So you could have a go at practicing this on paper now if you wanted, starting at A and doing a depth first traversal and a breadth first traversal and seeing the order that you visit the nodes in, only because you've got two tables in your EAD where you've got tables that look like they're single tables, and just a complete guess, but could be writing in the sequence that nodes would be visited if you were to do one of the traversals. Probably won't be, but could be, and it's not going to do any harm to revise. The solution for both, you've got the video links there to check against, so by all means just pause the video and work your way through those. Okay. The next question was on defining a graph. So what makes it? No, it wasn't defining a graph, was it? It was defining a tree. 3 things you need to remember for that. So a tree is connected, would get you 1 mark. Saying the word undirected and contains no cycles. They are the 3 things to recall, and you just needed to state 2 of those 3 things to get the mark. Okay, so that was that was sort of should be bread and butter marks there for that question. The next question, I may have been a bit harsh on marking, but it does emphasize a little bit of a point just to be aware of going into Monday's exam, which is make sure you try and relate your answers to the context. And describing a feature of a maze, a physical real world maze that would result in its graph not being a tree. So what they said in the mark scheme, I'll just put the mark scheme up. It said responses that clearly relate to a graph rather than a maze. So I think if you literally just said, you couldn't just put if it contains a cycle. You needed to at least kind of, and it's really semantics here. And maybe I've been too harsh. I don't know on 1 or 2 of you, but here the maze contains a loop or circuit would have got a mark because at least they've tried to contextualize it with a maze, and they've not used the graph term. There's no route from entrance to exit through the maze. So there you go. It was only a 1 mark question, but it is something just to be aware of on these questions where it's sort of applying sort of theory to a particular real world case. Just trying to make sure you do that explicitly. This question, everyone got this right, so I'm not going to spend any time on it. You're happy with filling in the adjacency matrix for the graph. And then explaining how recursion works. So everyone got this mark. That's fine. The second one is explaining the use of a stack in the running of recursive routines, isn't it? Now, this is the bit where you just need to remember those 2 key things to say. If you ever get a chance to talk about the stack and the call stack in particular, then you need to remember obviously the call stack, which we've got an example of over here, where we push each frame on, a stack frame on for each routine or method that's called. And remembering what's in each of those frames, what does each of those frames contain is where you get the first mark in this question. So that's your return addresses, the parameters and the local variables for each of these routines that are pushed on as and when they're called. So you got 1 mark for that, the understanding of what's held in the stack frames. And then the second mark, and I think the word to use here was about this reverse, this reverse order. So obviously in this example, main's pushed onto the stack. Main calls the subroutine print square, pushed onto the stack with its own stack frame. Print square calls square there, doesn't it? So we get another routine pushed onto stack with its own variables and parameters and so on. And then finally square calls multiply, and multiply is the one that actually does complete and return a value. And at that point, when the subroutine is completed, it's popped off, isn't it? So a lot of people said that popped off, and what I was really looking for, that word you want to use is returning to the previous invocation, or it reverses the order by which the subroutines were called, and it was that implication that I needed. It wasn't enough just to say sort of pop off, but it was about the return to the previous or the last stack frame to have been pushed onto the stack. Okay, so yeah, semantics, but important, and precision also important as well there. Here's the trace table, just the mark scheme. I'm not going to do the walkthrough of it. Obviously, we're hopeful on Monday that the tracing a Turing machine could be the trace table you're asked. Obviously, I deliberately didn't include a Turing machine trace table in this mock because we don't know that for certain. So it's good for you to practice, and it's good for you to be prepared for a trace table on any kind of algorithm. But like I say, I think if you're going to practice anything trace table wise over the weekend, practice the Turing machine questions that we've been given. Yeah, a lot of people were very close though to getting full marks on this question, and even people that only got 1 or 2 marks, you can see it was marked by box, basically 1, 2, 3, 4, 5, and some people were just very close and have, for example, have everything in correct here and would have just made a slight mistake in terms of the type up. Yeah, trace tables, love them or hate them, there's going to be something in there on Monday. So yeah, you can have a look over that and at your own discretion for that. Next question. These are the kind of questions where you should be getting marks, but people often aren't, and you've got to be precise and you've got to know your definitions. And this is just straight recall, static versus dynamic data structures. These were the kinds of things you should be saying in the mark scheme. Size, that was the word I was after. A lot of people said length. So I think size is the word you really want to be using there, and not leaving it open to interpretation. That's always the word that will appear in the mark schemes for these kind of questions. So most people said the obvious one. So the static structures have a maximum size, and you get 1 mark for just saying something along those lines, whereas the dynamic data structures can change. So you could get it if you sort of implied the point as well, but what you couldn't do is say static structures have a fixed size and then use this as your second point to say that dynamic structures can change. They're not 2 separate points, they're the same points. So that was something to be aware of. People did say things like the static structure size being fixed at compile time, whereas a dynamic data structure can change at runtime. That's quite a nice feature to kind of mention. But you could have other points as well. So the wasted storage space that's linked to static structures, whereas particularly if you've got a small size of items relative to the size of the structure you've used, and obviously dynamic structures only take up the amount of storage that's required to store the actual data. There is like caveat to that, isn't there? Which is the final point, which is per data item you've got to store the pointers next to the item, which static structures don't need. Yeah, but just check your wording on there, your precision. So lots of you'll be kind of probably a little bit frustrated you didn't get the mark there, and I've just emphasised some key words to make sure you're using for these kind of questions. Right, and then bubble sort, you just had to do the 1 iteration. This was the correct answer. Although I don't think this would matter in the exam, some people actually just did the trace table and didn't actually read that this is where you actually had to put the answer. and you were just showing what would happen to this trace to the values in this unsorted list as the result of one pass through it. So that's just something to watch out for, reading the question carefully, making sure you put your answers where you should do. But I don't think that'd be an issue in the exam, because in your EAD you would only have had access to this anyway. So yeah, just a little note to make there. And obviously with bubble sort on each pass, you know that the highest value will always be moved to the far right hand side, to the rightmost side of the list. So in this example, we compare the 18 against the 23, no change. The 23 against the 36, no change. 36 against 21, so we get the change there. And then we're comparing 36 against 58, no change. 58 against 40, yes, there's a change. And then 58 against 45, yes, there's a change. So you can see the mark scheme. So the fact that 18 didn't change got 1 mark. 23 followed by 21, because 21 did switch, didn't it, for the second mark. 21 followed by 36 got a mark, and then the final mark was showing 58 bubbling up to the end of the list, or second last element, because it wasn't the largest in there. Which algorithm was it? Bubble sort. I think hopefully most people recognize that. Time complexity for bubble sort being polynomial n squared, and the simple rule there is to remember, loop within a loop, likely to be very likely to be polynomial, which is what you've got with bubble sorts. And then the final couple of theory questions, again, really pleasing, most people getting these questions. So these were the words I was looking for: to write a program or algorithm that can tell, given a program and its inputs, without running or executing the program, whether the given problem will halt. And then the last one about the significance of the halting problem, the easiest way to say it, but still some people don't use this, is non-computable. Okay, it shows that there are just some problems that are non-computable. That would get the mark. Half of you did also say it just shows that some problems cannot be solved by a computer, which obviously is effectively the same thing. Okay, so for 1 mark there. Okay, and that completes the feedback for section A.